So dehumidification has a lot of importance, after COVID. But before COVID only, we invented an idea where dehumidification. We studied different problems in the air conditioning systems in India. So I'll directly go to the problem statement. So one of the problem is 90% of the air conditioned areas in India we don't dehumidify, just cooling only. So very few places around below 10% dehumidification is happening. That is the reason if we go to any air conditioned area, it's like not comfortable. So I'll explain about a 2 minutes video. After 5 minutes of my explanation, I'll show there what is the real problem. But if you see any hospitals, ICUs, they cool unnecessary more than the required. And also uh, buses and railway AC coaches, AC buses, we cool, but they don't dehumidify. Whereas in flights, dehumidification happens. That's the reason their ambient is comfortable compared to railway AC coaches or buses. Any factories or industries in India, particularly, they just cool, they don't dehumidify. That is one of the common problem. But after COVID, there is a requirement from all over the world, like that humidity shall be between 40 to 70% RH. Temperature is 24 to 30 degrees centigrade. So this is the requirement. When we see about this requirement, then there is a problem. I'll show you a small video where we can see the problem there. Let us take a problem. An example of office room with AC, 25 degrees is the set temperature. What happens when rain is falling outside? Humidity increases in the room.
Apache, your voice is not coming properly.
Okay.
Yeah, better now. Yes. Sure. And you can, click the entire, full PPT. Use full screen, yeah.
In addition to AC, high humidity in the room is a common problem when outside temperature is low or during.
Apache, your voice is again gone.
Sure. Okay. So I'm here is the office room where we have set temperature of 25 degrees centigrade. So if we suppose rain is falling outside, then what happens? Outside temperature goes below 25. So we see air conditioning stops running. So humidity starts increasing inside the room. That is the common problem. So what we did, conventional dehumidifiers, for example, desiccant dehumidifiers or compressor dehumidifiers, they have their own limitations. Particularly, compressor dehumidifiers we can't use in big areas, and desiccant dehumidifiers are really expensive. That could be the reason in India most of the places dehumidification won't happen. So we come out with some algorithms, and we developed a product concept, and that is approved by IASC, Indian Institute of Sciences, and they also supported technically to complete this project. We developed a product and we tested the product in environmental chamber and other places. So finally, we came out with a solution that we don't need to really cool the air-conditioned environment. Still, we can maintain 24 to 30 degrees and control the humidity where we see real a pleasant ambient condition, like in the flight, and we compared with the train, AC coach, and the flight ambient condition. Similarly, in all the air-conditioned areas, this concept can be applied. So that is about this solution which we have. That product is just heater along with the humidity and temperature sensors. So these combination of the simple heater and humidity sensors, yes, we can control the humidity and maintain the temperature within the allowed area of 24 to 30 degrees and 40 to 70% RH. So this is about our invention, and we completed the development. We're going to the market globally as well as national Indian market down the line. This is about it. If any questions, I'll answer. Otherwise, this is about the idea. So I can show a product. So it looks like this, a simple heater. When it goes to AHU models where sorry, are there any questions?
No, Pajay, you can continue.
Okay, so this is for a room. For example, even though simple concept, there are no standalone products available all over the world. If you install a simple heater, for example, we take a small room, this 4-panel heater with no air, just a panel heater, it will take care of humidity. It works along with the air conditioning. You don't need to set really lower temperatures. You can even set 26 degrees centigrade and 50% RH. You really see very comfortable ambient conditions inside the room. When it goes to a factory, and we have a AHU model where same like sensors and the heaters combination, depending on the air conditioning capacity we add, we don't need a really expensive dehumidifiers there. So that really reduce the cost of installation, initial investment, as well as power consumptions also, because when we don't need to really cool down, the air conditioning cost really comes down. So IAC really helped us, Indian Institute of Sciences, to complete this project. Last month we demonstrated all the technical papers. Now we're going to the production. That's all about this. Thank you for giving me opportunity.
Thank you very much for presenting the cost-effective solution to maintain the relative humidity in the room. Thank you, Apaji.
Yeah, thank you.
Yeah. You can close your screen and switch off your camera, please.
Sure, ma'am.
So next, I would like to call Dr. Rajkumar Velu, Assistant Professor from IIT Jammu, to present the research work.
Yeah, thanks, Dr. Neha. Here, I will share my screen now.
Again, position your camera properly. Correct position பண்ணுங்கப்பா.
Okay. Thank you, Dr. Neha. Is my screen visible now?
Yes, it is visible, and you can also, use the full screen.
Yes, I can. Okay. Thank you for giving me these opportunities. I am Dr. V. Rajkumar and Assistant Professor from Indian Institute of Technology, Jammu. And quickly, I will tell about my research experience. I have done my 3 types of postdoctoral research fellowship, and I've been working for additive manufacturing for close to decades. And now I am started working on IIT Jammu, and our core development is to develop me and and we are developing research center for additive manufacturing technology at IIT Jammu. And the core development, we are focusing on 3D printing machine. We are developing a homemade 3D printing machines, which is, whereas the commercial machines are quite challenging, and there is limitation of using materials, and that is limiting our research activities. So we are developing homemade 3D printing machines, which we are also focusing on integrating with artificial intelligence. That is where I have mentioned here. And the different additive manufacturing technologies, selective laser sintering, fused deposition modeling, and direct metal deposition. These 3 different or already commercially successful candidate machines, and we are developing our homemade, which is incorporating with artificial intelligence technologies. And our focus is on making a new materials, advanced materials, nano materials, meta materials, and various possible composites materials as well. And we are focusing for customized design, and eventually we are focusing on biomedical applications, aerospace, non-automotive applications as well. And the main objective is to gain a very good design and optimized design and topologies optimization and fabrication of any 3D structures or composites, particularly for lightweight applications. This is our core development and values. And when it comes to our evolution of Industry 4.0, so I have been following last 1 hour lecture. So we are all already been discussed with these type of images and what is 4.0. The understanding of my industrial 4.0 is like a cyber physical systems form the basis of Industry 4.0, and they use the modern control systems, have embedded software systems, and dispose of an internet address to connect and be addressed via Internet of Things. So Industry 4.0 is an intelligent networking machines and process for industry with a lot of information and communication technologies. So this is what we understood as a mechanical engineers and as a manufacturer design engineers, and we are like to incorporate these technology with additive manufacturing technology. And when it comes to the digital enterprise, so all these things have been digitalized, and eventually we are focusing on the real world or functional operational environment end use. And when it comes to potential applications, so first thing, it's based on the robotic based production, and there is maintenance. So far we discussed with Professor Dimitrios from Swinburne University, and he gave a laboratory research about the predictive maintenance. And the third part is an additive manufacturing of complex parts. These are not the potential implications of Industry 4.0. That's where we are focusing. And when it comes to the robots working on, this is an example, whereas Amazon is working a lot with this robots based, and they are successfully, implemented, and they are growing up and day to day their lives. And these are the key technologies which is focused in Industry 4.0. And our focus is in additive manufacturing, how it is have been incorporated with this Industry 4.0, and what are the other feasibilities of making other key technologies to integrate with this additive manufacturing technology, further to increase the production capability, otherwise to reduce the supply chain of manufacturing unit, or creating a smart or intelligent based manufacturing system. And the main impact what we focused is economy, business, national, society, and the individuals. These are the 6 key impacts which we identified based on incorporating additive manufacturing with other Industry 4.0. And when it comes to the role of Industry 4.0 and its technologies in additive manufacturing technologies, before telling that, I would like to give a brief introduction about the additive manufacturing technology. So additive manufacturing is nothing but a layer by layer manufacturing unit, where the existing or commercial, otherwise the traditional way is a subtractive manufacturing technology. And there are 2 stages. One is virtual stage and the physical stage. In the virtual stage, as you can see, all the system modeling, you can make any scanners or mathematical representation or any, what is that, MRI scan report that can be converted into 3D model, and that is all virtual stage. And this 3D model can be computational simulation and scientific visualizations can be done to understand more about the technical features. And then you can go for the additive manufacturing technology, where the machine is ready. It takes the input as a 3D model, and it will do a layer by layer processing to get an further functional end use product. And the commercially successful machines are selective laser sintering and FDM, or direct metal laser sintering, polyjet, etc. But nowadays we are all focusing on micro selective laser sintering process, or SLA, as well as the biofabrications for medical applications. And these are the different types of additive manufacturing technology. Mainly we can divide them into 3, that is solid based additive manufacturing technology, powder based, and as well as the liquid based additive manufacturing technology. From there we are splitting into different type of machines, and based on the component or based on the end use product, we will select an appropriate technology as well as the material application as well. If you are using a powder based one, we can use the second one. And in powder based, either it is a polymer or metal powder, we can do any type of materials with different type of additive manufacturing technology can be processed. And how the additive manufacturing process changes in manufacturing does. That is the main criteria we are focusing. That is low volume production, whereas any product is, if it is going to be a end use component, we are going to manufacture through AM process. So we can directly make a manufacturing process without doing any casting or molding process, and a material wastage is 100% is going to be avoided using this AM process. And we can do a mass customization. And the quick thing is rapid design iteration. So quickly you can make a rapid prototype of the functional end use products, so that it will be, you can observe the functional use of the particular product, and you can identify what are the failures, and quickly you can go back and adjust all the parameters, and you can take the prototype for iteration. No need to go for the end use component production for the research works. And there is a true prototyping product, and innovations, you can make as much as complex of the parts, so you can do all the optimization also. So these are the main advantages. And based on this, our project is proposed based on design and robotic fabrication of 3D composites. So we are incorporating robotic as well as the additive manufacturing technologies for a 3D composite technology. And this is like a digital manufacturing and design. And it starts from geometry, information acquisition, and digital design and computational engineering we are doing, then computational manufacturing. Then finally, it is going for digital fabrication and assembly. This is what our focus. Based on this focus, we proposed automated fiber placement process. That is nothing but there is a composite material fabrication technology, automated fiber placement process. These fibers, which is the black color and the gray color, when the black color fibers are carbon fiber and the gray color or the matrix, they are in the form of tape. They will be laying up on top of the mold surface. Okay. Once the mold surface is laid up on top of the material, the post processing will be done and the end use product will be taken out from the component. This is automated fiber placement process. And these are the some industrial automated fiber placement process will be undergoing. And yes, you can see there are the big, very huge molds have been using for this automated fiber placement process, and almost they are now using for robots for the AFP process, that is automated fiber placement. The research gap identified here is what about the mold material they are fabricating for this AFP process, because that is a separate supply chain and there is a separate manufacturing unit to create this mold surface. So to avoid and to create all together in a single unit, we propose to have materials for 3D automated fiber placement process plus 3D printing components. So I will tell you what is the proposal, and the material what we are focusing is if you use thermoset tape laying, thermoset material for the automated fiber placement process, it involves a different kind of things. And if you go for the thermoplastic, it will end up and there will be a supply chain shortening will be happening. And as I mentioned here, for automated fiber placement process, we are using a mold and we are placing on top of this. Preparing the mold, we are focusing a 3D printing system, and fabrication of 3D printed mold and tools involves on design freedom, low material wastage, and automated fiber technology. This is our methodology: design a composite parts, tool path planning, workshop setup, and the application on the prototype robot. And this is automated fiber placement robot. So we are planning to merge them together. Okay, so we are getting a very effective composite parts with a short duration and no need of a lot of expertise with them. How it is going to be fused together? So there are two robots. One is additive manufacturing robot and another one is automated fiber placement robot. This additive manufacturing robot is used to make a mold material. And once a mold material is fabricated here, this robot arm will be turned around and facing a automated fiber placement robot. That is robot 2. This robot will place, the fiber placement on top of the mold material, and it will go back for again 3D printing if it requires. Otherwise, we can place the fiber placement on top of it. We can take the component out of it. I will show you the principles how it works. This is additive manufacturing technology, whereas 3D printing is happening of the mold structure. Once the mold structure is ready, we are placing the fiber placement on top of it, and once this fiber is placed, we can turn around the robot for the again 3D printing, and you can see complete composite surface and structure is developed based on two robots without any hesitation, without time wasting, and without production time. These are the main focus. And after this, we did some experiments. These experiments, as you can see, we have faced some lot of defects. Whereas our Professor Dimitrios, he mentioned there is a monitoring and curing process have been conducted using the composite fabrications that is based on thermoset material. These are all thermoplastic material. So for avoiding these things, we are incorporating a machine learning system and going to improve the product, production rate, as well as we're going to get an end-use product with a complete, optimized, completely fused component. So the end-use component will be expecting in this way. So these are the some applications we are focusing: good aero, raptor wing, UAVs, furniture and lifestyle, and orthosis. So similar way, we are doing all sort of additive manufacturing technology. This is one form, which is robotic fabrication. The other form is selective laser sintering process, and as well as the direct metal deposition. That is also involved in different metal-based material also and end-use component. These are our research focus, and these are all we are doing for additive manufacturing technology along with artificial intelligence. Thank you for giving me these opportunities. You can contact me for any collaborations or research work based on these titles, whatever I discussed today. And thanks for Fusion 4.0 team for organizing this virtual conference and giving me opportunity. Thank you very much. Now it's open for you for any questions.
Thank you very much, Dr. Rajkumar, for reviewing the state of additive manufacturing and presenting its automation and workflow for increasing the quality and efficiency.
Yes, thank you.
For your time.
You are welcome.
The sound.
You are welcome. Yep. Thank you.
Thank you.